In this video, we'll be talking about Chapter 26 of Openstax Astronomy. And you should watch this after having seen the Chapter 25 pair of videos covering up the Milky Way galaxy specifically from the textbook. Because a lot of what we're going to talk about in this chapter will be referring back to the sort of foundational understanding that we built in the previous chapter. Now, there's been a couple of times over the course of the semester that we've talked about objects that have an M number. A couple of them showed up right towards the end of the chapter 25 slides, for example. And one thing that's really nice about this set of objects on our slide is it's all objects that if you have a backyard telescope or even pretty good binoculars, you can typically see all of these. Now, the set of objects itself came from Charles Messier, a French astronomer who was really interested in finding comets. So his goal was to find comets. What he would do is he would sort of scour the skies looking for comets, and he found quite a number of them. But helpful to us now, along the way, he kept track of the location and description of all of the objects that he came across that weren't otherwise identified as single stars. Those are just points of light, very obvious to us. Planets, those have been known since ancient times, and we can tell the difference between a planet and anything else. And then, of course, he didn't include comets in this set because he was publishing his results of those elsewhere. So this became the Messier catalog. And if we look at even just the tiny pictures here, and you can also just Google the Messier catalog and look up a bunch of those yourself. But if we look at this set, what we might notice is that a lot of them seem like they are just star clusters. And that's because a lot of them are. Star clusters, especially globular clusters or globular clusters, those are easy to find with a telescope or pair of binoculars because there is so much light coming from that single point in the sky because it's hundreds of thousands of stars in our galaxy, so not too far away from us. The other thing you might notice is that some of these look like familiar nebulae that we saw in our chapter 20 slides, and that's because they are. The Pleiades is in this set. The Trifid Nebula is in the Messier Objects Catalog. The Orion Nebula. All of those are here as well. And a couple of the planetary nebula and supernova remnants that we talked about are also in this set. So the Crab Nebula is here. That was a supernova remnant. Some of the more nearby planetary nebula are here. And once you take out some of the things that we've talked about in previous chapters, so star clusters, nebulae, what you're left with are galaxies, right? We can even kind of point at ourselves several of these that are very clearly galaxy-shaped. And the really important thing to recognize, and the reason I've started with this kind of anecdote, is because in the 1700s, when Charles Messier made this catalog of objects, we didn't actually know that these were other galaxies. So we talked in chapter 25 about how we discovered the Milky Way galaxy, and that took having distance measurements to Cepheid variables in globular clusters to be able to get a sense of the overall size of the galaxy. But what we also need to recognize is our ability to talk about other galaxies relies on our ability to make distance measurements to other galaxies outside of our own. Now, when we think about Henrietta Leavitt's work on Cepheid variables that we talked about, and Harlow Shapley helped to make it the period luminosity relation, and then he did that map of the globular clusters, that started the wheels turning on getting distance measurements to even farther away objects. Now, kind of, if we think about the history of things, and memorizing years in this class is never something that's important. But I'm trying to give us a sense of how recent or far back in time some of this stuff is. So Messier in the 1700s built this catalog of stuff that he could see with his telescope. And remember, that was around the time when we're starting to get the better telescope technology that we talked about in Chapter 6. There was a big debate in the year 1920, basically a town hall full of people and two people standing at podia yelling at each other, right? Any good debate. And it was basically between two scientists, Harlow Shapley and Heber Curtis. Heber Curtis, born not too far away in Muskegon, Michigan. And they basically disagreed on what those spiral nebulae were in the Messier Objects Catalog that were visible in the skies. Now, we're calling them spiral nebulae because they could be smaller objects that are close to us or galaxy-sized objects that are really far away. Without a distance measurement, we can't make the distinction between those. Okay, so there was a grand debate held in 1920, and although it was a long debate and there were a lot of complex nuances to it, we really can summarize the issues kind of like a Student 1, Student 2 debate that we see throughout our lecture tutorial books. So I want you to think about this the way that we do throughout the lecture tutorials and decide who you agree with, if either, and why. So pause the video and read through the sort of main statements, and I'm certainly putting words into their mouths, but that's the main gist of their arguments. I want you to think through and decide who you agree with. Okay, so hopefully you paused the video and thought through it. If not, now's your chance. But the problem is, in 1920, we just did not have enough observations to be able to fully rule out these two arguments. What we now know, right, fast forward 100 years in the future, what we now know is that we are near the edge of the Milky Way galaxy. Harlow Shapley's map of the globular clusters was a valid map, but all of those spiral nebulae are actually galaxies way outside of our own. So Harlow Shapley was right about our location within our galaxy, but not about the size of our galaxy, the extent of it. And Heber Curtis put us at the center of the Milky Way. He didn't agree with Harlow Shapley's globular clusters map because he thought that a lot of those were outside of our galaxy too, and decided that our galaxy was really, really small and everything was way outside of ours. So both of these students, both ideas of the debate were incorrect because only part of their idea was right, and so their full statement is not correct. But again, it's not really through fault of their own. They didn't have enough evidence to be able to rule out the bad ideas. The big break came just a couple of years later with Edwin Hubble, for whom the Hubble Space Telescope was named, when he was studying variable stars in Andromeda Galaxy, which at the time was Andromeda Nebula. And what we're looking at here on the far right side is a map or a photographic plate that is inverted color, and it's got little notations that Hubble made because he was studying nova. Okay, so pause our thoughts, but listen to me. Pause our thoughts. Okay, nova we've talked about back in chapter 22 or 23. A nova is a white dwarf that's in a binary system and being given some material so that it can flash fusion, a bright flash of light, and it can go through that process multiple times because the binary might still be throwing material onto it. Hubble was studying these and traced them enough to realize that one of the stars or star systems that he had identified as a nova, and again, it's a star system that's too dim to see normally unless we're at the sort of brighter flash. He identified that one of those was actually a Cepheid variable, the same category of stars that Henrietta Leavitt had first studied was in his set. At this point in 1923, this was still very early on in the period luminosity relation, and it hadn't been fully, properly calibrated. So his announcement, the published paper that he had for that work, said that Andromeda Galaxy was 900,000 light years away. Okay, so that galaxy, that is a huge number, even for being wrong by too little. We actually now know that Andromeda is 2.5 million light years away from us. And so, even with that smaller incorrect number, in 1923, everyone realized, holy smokes, our universe is so much bigger than we thought. And these things that seem like they were nearby spiral nebulae are actually galaxies way outside of our own. Now, Milky Way galaxy, our own galaxy, has some nearby neighbors. Andromeda is the only really large nearby neighbor, and it's part of what's called the local group, basically a set of galaxies, Milky Way, Andromeda, and a bunch of smaller ones like the Large and Small Magellanic Cloud, that are all gravitationally bound together. Now, I saved this lecture tutorial that we're about to think about. Either if you're in the flipped classroom on campus, we'll be talking about this next time we meet. If you're in the online class, this is the right time to try it, either after this video or even just pausing it and trying it. Because we want to build up an understanding of galaxy size scales in a way that we haven't had a chance to before chapter 25. One note about this lecture tutorial, we need a ruler that has millimeters and centimeters on it. So if you don't have that, it's okay. We won't lose too much learning with this, but it really will help us set the stage for just how big the Milky Way is. After we try that lecture tutorial, this question will be easier possibly to answer, especially because that will remind us again of the local group, but we did define that on the previous slide. But this is a pause and think question for us that we should be able to answer even now without the lecture tutorial. Which of the following lists objects from largest to smallest? And this is incredibly important to get correct because it helps us connect ideas from different chapters together in our big picture understanding of what we're learning about this semester. So pause the video and think about it. Okay. So first of all, local group on the previous slide we identified as a set of galaxies. So right away from that, we can rule out any of the options that put galaxy as being larger than local group. If local group is a bunch of galaxies, then it is larger than a single galaxy. So 3 and 4 we should have ruled out right away. And if you picked those, then I really do urge you to kind of rewind, make sure that you recognized and maybe even wrote out the definition of the local group. We'll be revisiting it in this chapter, but it's something that we need to kind of keep on our radar. And so now we're left with options 1 and 2. Globular cluster, it kind of sounds like galaxy cluster, and a lot of students kind of forget that we learned that term several chapters ago. Globular clusters or globular clusters are a star cluster of hundreds of thousands of stars, but galaxies contain hundreds of billions of stars. Our Milky Way, we talked about in our chapter 25 video, has about 150 of these, or it has a finite number of these globular clusters. And so, number 2 we have to rule out because a globular cluster is smaller than a galaxy. We have those inside the Milky Way galaxy. For number 1, if you were a little bit concerned on whether a nebula or a star is bigger, we need to remember that the solar nebula theory talked about how this bigger cloud of gas and dust collapsed to form our star, which means that the bigger cloud of gas and dust is larger than a single star that it can possibly make. And most nebulae that we've talked about are so much larger than just one star's worth of material. So number 1 is the correct answer here. And if it was something that you didn't get correct or something that took you a long time to get to, it's worth making sure that we realize that all of the terms on this slide are ones that need to be in our vocabulary to be able to build this intuition for sizes. The other thing to note is we didn't have to look up the physical sizes, printed sizes of any of these objects to put them in order. And that's a really important distinction between memorization and critical thinking. Okay. So, the Milky Way and Andromeda are both spiral galaxies. And the Milky Way is a barred spiral galaxy. We introduced that back in chapter 25. But the next couple of slides are kind of a quick photo album or sort of family album of the different types of galaxies that exist, because it's useful to have an understanding of the fact that we're being very distinct about the Milky Way being a barred spiral should tell us that there are other types of spirals and other types of galaxies that aren't a spiral. Okay, so the Whirlpool Galaxy. First of all, if you've printed the slides, you won't see this particular picture. And if you're looking at the video now, you might be thinking to yourself, that's kind of like some blobs. But I want to give us some context. This is an image that students of mine took in 2014, and we were using a fairly small telescope on top of a science center in Cambridge, Massachusetts. That is literally across the river from Boston, and so we're dealing with a fairly small telescope, low light gathering power, and a huge amount of light pollution. Okay, it took us several minutes of just gathering photons from this galaxy to be able to make the picture that we're looking at. And we did this with different wavelengths and made a color picture, but that's not the point here. The point is that you can see these kinds of things, and this is what your eye would actually see through a telescope or through binoculars. And it's worth making sure we kind of have that understanding that the pictures that we're going to be seeing from Hubble, this one, they do enhance our ability to see structure beyond what our eyes would actually be seeing. Because even with really dark skies, this is what our eyes would be seeing. And I'll go back and forth between the two. And you can see that the structure is there, especially now that you can see what it's supposed to look like. And the main distinction is the light gathering, and then with the Hubble Space Telescope, they're putting multiple wavelengths together, including outside the visible, to be able to make a image that our eyes would not be able to see, but that is still trying to indicate real structure and real phenomena. As an aside, the Whirlpool Galaxy is one of my absolute favorite galaxies. The M51 name on it is indicating to us that that's part of the Messier Objects Catalog. And you can actually see that there are two separate galaxies here, and they're in the process of merging. To be an even more extreme example of a barred spiral, because the previous example was just a regular spiral, unbarred. Barred spiral galaxy, this one NGC 1300, means that it is a galaxy that was not identified by Charles Messier, which what that tends to mean is that it is farther away and harder to see, and so a backyard telescope wouldn't be able to see it, but Hubble can. And again, we're kind of highlighting structure here beyond what our eyes could see. But this is showing a really, really clear bar and just a sort of half turn of the spiral arm pattern around that. It's important to recognize that when we're talking about spiral galaxies like M104, another part of the Messier catalog, that we can still identify it as a spiral galaxy even if we don't actually see the spiral arm structure. Because one really important aspect of spiral galaxies is the fact that they have a distinct plane of material in a disk. And this image is very clearly showing us the disk of material, even a sort of dark band, because that dust in the disk is blocking the starlight behind it. So even on edge, we can tell the difference between a spiral galaxy and a non-spiral galaxy. Okay, but up until now, as you've noticed, all of these have been spiral galaxies, so why haven't we been showing you the other main type? That's because they're kind of boring. This is M87. It doesn't even have a cool name because it's just like a giant blob. And it is a classic example of an elliptical galaxy. That is the other main type of galaxy, spiral and elliptical. It highlights for us why we don't really think about elliptical galaxies when we're kind of sketching a galaxy, right? If I had you do like a 20-second sketch of a galaxy, you'd draw the spiral arms because they're cool. They look distinct. They look galaxy shaped. This is galaxy shaped too. Ellipticals are actually more common than spirals, but they basically are just big spherical collections of stars and not much else going on. There's no spiral arm structure. There's no defined disk. It's just random star orbits around some central area. You can have really big elliptical galaxies. You can have really small elliptical galaxies. And in all of those cases, they're just kind of blobs of stars. The giant elliptical galaxy on the left has more than 10 times the mass of the Milky Way. And on the right, we have one of these dwarf galaxies, these smaller galaxies, that is part of the local group, the area around our own galaxy. So kind of neat. This picture is really cool. It is not a view that we would have access to from Grand Rapids, Michigan, because what we're seeing here on the left side of the picture are the small and large Magellanic Clouds. Those are actually irregular galaxies. They don't fit a spiral shape and they don't fit an elliptical galaxy. They aren't a spiral because they don't have a single flat disk, and they aren't an elliptical because they still have a lot of gas and dust. Ellipticals don't. Dwarf galaxy is kind of a rough definition, but usually we mean less than about 1 billion stars. That's still significantly smaller than the Milky Way with 400 billion stars of mass and about 200 billion actual stars. Okay, so lots of cool pictures, and what it comes down to is that there's really two main types of galaxies. Spirals have a lot of gas and dust, and we can kind of see it in images. They have ongoing star formation is happening in the spiral arm structure. They have a net rotation and a nice flat disk in the most part that mixes metals in. And about 1/3 of all galaxies are spirals. About 2/3 of those spirals are barred, like our Milky Way. Elliptical galaxies, on the other hand, is basically the opposite of all of that. They've lost their gas and dust. Because they don't have gas and dust, can't easily make new stars, so they're mostly composed of older, redder stars. The reason we say redder is because the colder stars on the main sequence are the smaller ones, the lower mass ones that live longer. The hot, bright, large mass blue stars don't live very long and they go away. Elliptical galaxies don't have a net rotation. It's all random orbits all over the place, and about 60% of all galaxies are ellipticals. And as we continue forward in time, we're going to be seeing more and more elliptical galaxies. And we'll talk about that in just a little bit. There is a way to classify galaxies called the tuning fork diagram. It comes from Edwin Hubble. And when Edwin Hubble originally identified this tuning fork diagram, he kind of used it as ellipticals turn into spirals, and that is 100% not the case. Ellipticals don't have gas and dust. They can't magically have a whole bunch appear. All of these random orbits, there's no process to have them settle out into a flat disk. But this galaxy classification scheme still is a really clear way of kind of distinguishing the two types, and the fact that spirals have barred and unbarred. And the sort of middle ground would be a galaxy that is mostly a disk shape, but doesn't have gas and dust. Okay, now that we've identified that there are different types of galaxies, we really do want to try to use that information to classify galaxies. This is the right time to try the lecture tutorial galaxy classification online, either at this point or after this video. On campus flipped classroom, this would be something that's going to come up the next time that we see each other. Worth noting, it's not just pages 139 to 142, it also uses the inside of the back cover of the lecture tutorial book, which is the only place that's printed in color. So there you go. A pause and think question for us that will be more easily answered after the lecture tutorial and some of the student discussion questions that show up there. But try it anyway. So pause the video once you've read through the options, or pause the video in order to read through all the options, and then vote. So a galaxy that appears to be populated by mostly red stars, likely what? So pause and think. Okay. Let's go through these top to bottom. So for number 1, never having blue stars is not a possibility. Galaxies can never pick and choose what types of stars they make. They make all types of stars. Smaller stars are more common than bigger stars, but they can't just choose not to make those large, high mass, high temperature stars. Number 2, had blue stars that are not present anymore, but were a long time ago. That sounds pretty darn good, right? Why are those blue stars gone? Because high mass stars die first. Number 3, has been around long enough for blue stars to all evolve into the red main sequence stars we see. This is a very commonly chosen answer, and usually it's because we read too quickly. Because if we think back to stellar evolution, all of the chapters that we built an understanding of stellar evolution, never ever did stars move up and down the main sequence. They always left the main sequence to become red giants or supergiants, and then exploded or became white dwarfs. So never do blue stars become red main sequence stars. That's really important for us to recognize. If you picked it, it's probably because you read too quick, and that's okay. Number 4, never contained enough gas to have blue stars develop. That's just a more sciencey sounding wording of number 1. Still wrong. And number 5, has blue stars that are being blocked by dust. We talked about the fact that dust does make stars look redder, but we can still identify that those stars would be there, and that isn't why these galaxies look red. So number 5, it isn't an explanation for why these galaxies look red. So the answer here is number 2, and if you answered 3, hopefully it's because you read too quickly and not because we're kind of misunderstanding stellar evolution. If you did pick number 3 because we're misunderstanding stellar evolution, it'll be worth going back to some of those videos. Okay. Worth recognizing, and this is something that came up at the end of the lecture tutorial, and I mentioned it briefly before, galaxies cannot go from one type to another if they're just by themselves in space. A spiral galaxy, no matter how long we wait, is not going to become an elliptical all by itself. An elliptical galaxy, no matter how long we wait, is not going to become a spiral galaxy by itself. But what can happen, and what we talked about happening at the very end of chapter 25 slides, is that two similarly sized galaxies, if you merge them together, and these are all snapshots from a computer simulation, two similarly sized galaxies will result in an elliptical galaxy. All of the gas and dust will either form stars or will be flung out. It's too low mass for gravity to kind of keep hold of it. And you end up with a big blob of stuff, and you lose that spiral galaxy structure. Okay, so the last couple of slides are helping us to get a sense of larger scale distances. Now, Cepheid variables helped us get the distance to Andromeda, but that's in our local group. For further away objects, for further away galaxies, they're too far away to be able to find a Cepheid variable in that light that we're receiving from the galaxies. Instead, we can look at their Doppler shift. So yet again, another way that Doppler shift is used in astronomy to help us figure things out. Now, Vesto Slipher was looking at Andromeda Galaxy well before Edwin Hubble actually measured its distance, because remember, really important, Doppler shift does not tell us about distance. Really important. What it does tell us is the speed and direction of objects that are moving. Blue shift means towards, red shift means away, and the amount of shift is telling us about the speed. And so he identified that Andromeda was moving towards us. Remember, Andromeda is on a collision course with the Milky Way, so that's something we talked about, but that's how we figured that out. The key thing is that Slipher followed up with a bunch of these spiral nebulae. Again, we didn't have distances yet. We're kind of going back before that identification. And what he realized was objects of this type, these spiral galaxies, spiral nebulae, which we know are galaxies, What he saw was that all of them, besides Andromeda, were all moving away from us. The ones that looked bigger were moving kind of slow. The ones that looked smaller were moving pretty fast. Now remember, if all of these galaxies are roughly the same size, what would it mean if they look smaller? That's exactly right. It's farther away from us. So a smaller looking object is farther away. And so what we're finding here is that the farther and farther away galaxies are, the faster and faster they appear to be moving away from us. Edwin Hubble plotted velocity versus distance for the galaxies that were close enough to get measurements with Cepheid variables and similar processes. And then he teamed up with Milton Humason to be able to improve on his data. We can see the big scatter in the 1929 data, and that same set of points is drawn in part B to show just what we were able to add with more distant objects. But what we're seeing is a nice straight line through that data. That's important to us. That shows us Hubble's law. Hubble's law is incredibly, incredibly important for us, more so in chapter 29. But it is another method for determining distance to objects, because Doppler shift we can fairly easily do. That gets us the velocity. The h-naught value is the slope of this line. It's an identified number. And then we can actually figure out the distance from that. Some questions you may have: why are these galaxies all redshifted besides the local group? They're physically moving away from us, Doppler shift. Why are they moving away from us? Well, the universe is expanding. Okay, now you should be asking yourself, why is the universe expanding? And that is a great question, and one that we're going to save for our chapter 29 video. So the last thing that we want to talk about before we wrap this up, and then our next video will be thinking about chapter 29, and that's going to be next week. We want to make sure that we have an understanding of our place in this larger structure that we're starting to understand. So we're part of our solar system, which is part of the sort of solar neighborhood that we're in, which is part of the Milky Way galaxy. And the Milky Way galaxy is part of the local group. This picture here is trying to indicate to us three-dimensional distances of the local group, where we've got the Milky Way galaxy plane in this kind of purple angled square, and the volume of distances farther and farther away from us, including 500 kiloparsecs. Doesn't mean much to us, but the point is that sphere that we're drawing, Andromeda's outside of that, but still part of our local group. All of these galaxies here, we don't have to memorize them, but we see SMC and LMC for the Small and Large Magellanic Cloud. We see Sagittarius Dwarf Galaxy, that's the one being eaten that we talked about in chapter 25. And then Andromeda is the only other major size galaxy in our local group, and it's on a collision course with us. If we go to larger scales, we start to understand that space is really, really big. The local group is the name of our galaxy cluster. So local group is the specific name of a structure called a galaxy cluster. It's actually a fairly small cluster. It's like we're in a neighborhood, but we're kind of near a larger city. The largest coherent structure in the universe that we can really say that we're part of is a galaxy supercluster, which means a cluster of galaxy clusters. We live in the Virgo supercluster, named after the largest star cluster that it's part of. Now, what about even larger scales? At this point, we start to reach the largest scales in the universe, which gets to the point that the universe is actually infinite in size. And that's something that we'll be confronting and dealing with next week. But we have a computer simulation that shows us the sort of largest scale structures that we can think about in the universe. And this video I'll have linked in Blackboard. But it runs through the 14 billion year history of the universe and how this structure, this kind of web-like filamentary structure that we see on this press release image, formed. In the observable universe, or the visible universe, there's over 200 billion galaxies, each with roughly 200 billion stars. And that's just the part that we can actually measure with telescopes. So, chapter 29 is going to be getting into the really big picture ideas. And just to wrap up the last couple of slides, our universal address is the way that we describe all of these structures that we're physically a part of. So on Earth, we can give people our address, right? We give them the street address, the city, state, country. But if we wanted to add to that, to be able to have a pen pal on the other side of the known universe, we would have to add the fact that all of that information, the fact that we're here in the US and Michigan, we're on Earth instead of Mars or Jupiter. We're in the solar system instead of some other star, the Vegan system or, the Polaris system. We would say the solar system, solar, that means sun. We would have to indicate that we're part of the Milky Way galaxy instead of Andromeda galaxy. We would have to indicate that we're part of the local group instead of the Virgo cluster or any other cluster. And then this image is a little bit older. It calls it the local supercluster. That's fine, but it's actually the Virgo supercluster is the agreed upon name for the larger scale that we're part of. With all of that, and I know it seems daunting, and it kind of should seem a little bit overwhelming, the main thing I want us to understand is this picture kind of highlights all of the scales that we've talked about up until this point. We thought about the Earth and the planets in our solar system in the first portion of the course. We thought about the stars that are outside the solar system but inside the Milky Way. We thought about all that star formation idea in the next part of the course. And this week and next is our chance to think about the largest scales. The fact that galaxies are these kind of island universes almost, but galaxies are a particular term for a scale that is larger than solar system, but smaller than the infinite single universe that we're part of. So, a lot to ponder, and we'll pick this back up in chapter 29. We're not going to cover chapters 27 or 28 in this course. We'll pick this back up next week with chapter 29, thinking about the universe and all of the big picture ideas. I'll see you then.